Good morning, everybody. Welcome to my presentation. Today I'm going to present a joint work with Chris Knight at Dartmouth College. And we study a group of statistical tests in economics that we call Sniff tests. We're all very familiar with the canonical form of publication bias, which Abel just talked about extensively. So here we are going to shift the focus to a group of tests that we call Sniff tests. Those are tests that are balance tests, placebo tests, and specification tests, and extra, where the author's incentive is quite the opposite from the canonical statistical tests. In this case, the authors would favor the statistically insignificant results. And we think this will offer a new window into publication bias. There's a major advantage of studying this kind of test because the p-value from balance tests in RCTs, if the authors have not taken valid measures to improve balance, have a uniform distribution between 0 and 1 if publication bias is absent. So this allows us to use reduced form methods to test whether publication bias is present and to quantify the effects. And for other types of types of Sniff tests, we don't know the underlying distribution, but we can use structural estimation using specifications informed by our reduced form approach. And here's a graph of the number of Sniff tests over the years in our sample. You can see from 2005 to 2015, there's a rapid increase in the number of the use of Sniff tests, giving us more reason to study the publication bias in this set of tests. Our data consists of an initial pool that we search over relevant keywords on ScienceDirect, and then we supplement Elsevier journals that we found on ScienceDirect with top 5 general interest journals in economics. We then asked research assistants to scan candidate articles to verify whether they contain tables of Sniff tests, and if so, collect detailed information associated with the table of test statistics. Only 2 such tests are included, and our final sample includes almost 30,000 Sniff tests from almost 60 journals. And here's a detailed sample breakdown in our sample. We first have a special place for the RCT balance test because we know the underlying distribution absent of publication bias. And then we group all other types of Sniff tests together. And we know there are valid measures to improve balance for RCT balance tests, namely re-randomization, stratification, and matching. So we take extra care to separate cases where we know that such methods are employed and where we know that it's a priori impossible to improve balance using these methods. And for other tests, re-randomization and stratification don't apply, so we separate the pure cases where no methods are employed and samples that are pre-match and post-match. And we also collect data such as whether the exact p-values are reported or only the interval, by position in the article, whether it's in the body or appendix, by whether the test statistic uses symbols to highlight significance or not, by the tier of journal. We used a 5-year impact factor from the Thomson-Reuters journal citation report, and by authors' confidence about the performance of Sniff tests. So by strong claim is when the authors are confident about their Sniff tests do well, and when the table contains some significant Sniff test results, they explicitly attribute that to random chance. And by weak claim is the case when there are a few significant test statistics in the tables, and the authors mount some defense for the validity of their test, often citing the reason that even though there are some significant test statistics, there is no systematic pattern, so it doesn't undermine the strength of their main results. And when authors say nothing about test statistics, it falls in the third category, and when they freely acknowledge the failure of their Sniff test, it's in the fourth category. And our reduced form method is straightforward, mounting to visually inspect kernel density of various subsamples of p-values, and a simple test of equality by comparing the average proportion of p-value significant p-values in a table to the null, which is the uniform distribution. Then we quantified the departure from uniformity at different thresholds using two approaches. The first approach supposes the p-values proportions exceed the uniform benchmark by a constant level at each of the three conventional thresholds, 1%, 5%, and 10%. And for approach 2, we suppose the p-value proportions exceed the uniform threshold by a constant proportion at each threshold. So here are our kernel density estimates for the distribution of different subsamples. Here is the full sample, and just by staring at this, one might get the conclusion that it's very different from the uniform distribution, and there's a huge mass between 0 and 10%. A very simple and naive conclusion would be that there's no publication bias at all, and quite the opposite. There's a huge mass suggesting a lot of significant Sniff tests. But if we zoom into the RCT balance test, we can see that somewhere between like 0 and 0.1, the mass is like below the uniform distribution, and then it rises in this region and it follows uniform distribution more closely. And the distribution that follows the uniform distribution the most closely is the sample of RCT balance tests where it's possible, like techniques to improve balance is possibly employed. And for all of our tests where no balance improving techniques are employed, we see something similar to the full sample. And this might suggest that, this first does not suggest that there is no publication bias. Rather, we think there are two forces at play that generate this kind of kernel density. The first is that there's a huge number of studies that have study flaws that are picked up by Sniff tests, but the publication bias might still be present that removes a portion of that. And evidence would be that this, even though here is a huge mass between 0 and 0.1, we see a discontinuity in this region. And for our structural model, I will explain, our structural model would be able to explain a density that looks like this. And for other tests, pre-match, as expected, the Sniff tests perform pretty poorly, probably the reason why the authors then would use matching techniques to improve balance in the first place. And post-match, the Sniff tests indeed perform pretty well, suggesting matching is an effective method to improve balance. And then this is a table 2 of our paper, and it formalizes what we observe in this kernel density plots, and all the results are qualitatively and quantitatively pretty similar to the density. And here for the pure cases of RCT balance tests, we see that at 10% threshold, the mass of significant p-values is quite different from the 10% benchmark predicted under uniform distribution. And for the pure tests, other types of tests, we see a huge mass between 0 and 0.1. We then test the heterogeneity across categories, such as body versus appendix, whether the test use symbols to highlight significance versus no symbols, top journals versus lower tier journals, etc. And reassuringly, we find that the authors do not appear to hide significant test statistics in appendixes or obscure them by omitting significant symbols. But there's some evidence that Sniff tests are less significant in top-tier journals, in smaller articles, and in more recent articles. We also inspected the fine-grained histograms of p-values and found no evidence of authors manipulating to reduce significance of Sniff tests around the key thresholds. These results are all conditional on that these test statistics are being published. And then motivated by what we observe in the kernel density plots, the huge masses between 0 and 0.1 for other tests, for pure cases, other tests, we asked the question, do authors over-attribute significant test statistics to random bad luck? So we have 4 categories in terms of the author's confidence in the performance of their sniff test results. So for the RCT balance test, when the authors are confident, the proportions are indeed smaller than the benchmark proportions. But for the other test pure cases, when the authors make strong claim, especially at 1% threshold, we're observing like doubling the amount of what we should observe if the test statistics indeed follow a random distribution, suggesting that the authors might be over-attributing test statistics to random bad luck. And for weak claims, we're seeing that like when the authors make a weak claim, the proportion is no better than when the authors make no claims at all. So testing whether the proportions of significant p-values are similar across different categories of other claim as expected, all of the other categories are different except for when there's no claim and when there's weak claim. The proportions are pretty similar. And here comes to our structural analysis. We specify a simple two-stage model that captures the characteristics of the kernel density pretty well. So in the first stage, we specify a random beta distribution with one single parameter to describe the rate of study flow. When this parameter m is equal to 0, there is no study flow, and this prior density reduces to the uniform density. In the second stage, there's a proportion b of p-value significant and some cutoff level alpha hat is removed from the published sample and apply Bayes' rule to the prior density. We get observed density in the sample. And predicted by our structural model, those are the p-value densities generated by our model. When there's only study flow and no publication bias, we would see a distribution that looks like this. And when there's only publication bias and no study flow, we would only see that there's a mass removed between 0 and 0.1, and the rest follows the uniform distribution pretty closely. And when the two forces are both present, we see a spike over here and the discontinuity over here. And then notice that those densities generated by our model follows our kernel densities plots pretty closely. And our structural estimates for the RCT balance test pure cases, we use maximum likelihood to recover those parameters, and this suggests that the study flow parameter for this subsample is not significantly different from 0 as expected, and the publication bias parameter is around 45%. And compare this with the reduced form estimate that I presented in table 2. The implied B tilde from table 2 is within a few hundreds of the structural estimate, giving us confidence that our models correctly specifies the two forces that we think are present. And for other test pure cases, we have a huge parameter for study flaws, and the publication bias parameter is over 90%. So here comes to the end of my presentation, and let me summarize what I just presented. For the pure sample of RCT balance tests, nearly 45% of significant RCT balance tests remain in the file drawer, and pure sample of other tests, for the pure sample of other tests, there's a substantial number of study flaws picked up by sniff tests, and the structural estimate implies over 90% of the significant tests ended up in the file drawer. Reassuringly, for this published sample, we do not observe evidence of author manipulation. There's some evidence suggesting that sniff tests are less significant in top-tier journals, in smaller tables, and in more recent articles. And then we also suggest carefully interpreting author claims is needed. The authors tend to make overly strong claims that the results are due to statistical noise, and the weak claims, if anything, is a worse signal about the performance of sniff tests compared to when the authors make no claims at all. Okay, thank you. Is there any question from the audience?
One question. Sorry. Sorry. Quickly on the pure RCT balance tests and the over-representation of low p-values, I'm wondering how many of those are small experiments where
Oh.
the p-values themselves probably are have a incorrect false positive rate.
In our study, we do not separate like experimental studies or just like RCT so the RCT balanced has like, we don't separate
Yeah,
like.
you could just plot like size of experiment by these p-values, and then you'd learn if perhaps people are using, even their individual balance tests probably shouldn't be used in the same way.
Yeah.
Like, you know, two small clusters, not adjusted, things like that.
Okay. Thank you for the suggestion.
Great, thank you.